Our last video from 3.2 is brought to us by Saruman from Lord of the Rings. He was evil all along. So our author here is asking us to do a little calculus, which is a bit crazy. So we're going to kind of skip past it. I'll just highlight a few things. We're taking the compounded n times per year formula, and we're just going to substitute in an expression for n that's n divided by r. We're going to call that u, and it becomes this, and you're asking why, and we're like, because it's going to do something special, and that's a thing that mathematicians often do. We change one thing in for another thing, and it allows us to rewrite things and make things simpler, and we do all this stuff, and suddenly we get to this really nice expression that looks like this. And what we're really getting at is this part right here is related to the y equals a times b to the x formula. This is what's familiar to us. And this b was the factor in exponential in the exponential models from before. And what our author is saying is, hey, let's mess with this thing. Let's put in numbers here and see what happens as in this expression as we get numbers that are larger and larger and larger. We plug it in there. In other words, we do 1 plus 1 over 50 raised to the 50 power. What kind of special thing happens? We're going to do this in Desmos real quick and just have you note what happens with this screen or with this particular thing. So I'm going to do 1 plus 1 divided by, I'm going to use x here just because Desmos tends to like x over u's. We could have used u. Now I wrote it in as an equation, but I'm going to actually turn it into a table. Whoops. It's a nice little trick you can do. And then I can type in those numbers we wanted. 50, 100, 500, 1,000, 1,500, 2,000, 2,500. Let me hide this actual graph that's happening here, and we'll get a zoom fit thing. I'm going to go to 5,000. I'm going to add a few more things in here, and 10,000, and I don't know, let's do 20,000 just for fun. And you can see what's happening. Our expression or our numbers are getting closer and closer to a particular value. It looks like 2.7182 something something something. Surprise, it's the number e. It's called Euler's number. It's a special number kind of like pi that you may recognize from a former class in your life. It's a number that occurs out in the world. It's an irrational number, and it tends to model particular things. And for us, it models things that are compounded continuously. What we mean by that is it's items, or it's things that happen infinitely, like every instant of every moment of every day. Things that are just compounded over and over and over. So note, we've discovered this number e. It's approximately 2.718. And I'll write out the calculus of this. You do not, this is just for fun, y'all. I'm just saying, hey, if you ever want to go further in math, check out some calculus. What we're saying is, as we make this u value really, really big, infinite, this thing is infinity. Again, this is just special fun. You don't need to really know anything about this. This is way outside the scope of this class. As we make this get really, really big, this equals exactly the number e. In Desmos, you saw that. I typed the number e, and Desmos spits out this number, 2.718, etc., etc., etc. Okay? So you're going to use that when working with things. And our author does not give us a compounded continuously formula. So I'm going to write it down here. If something were compounded continuously, it would look like this. The future value is equal to the principal times e. Note, this is a number, raised to whatever the interest rate is times the time. That's how we would calculate the future value of an account compounded continuously. Now, this doesn't really exist in the real world, so this is just a fun little side note. Things that are compounded continuously out there in the world are like populations or the radioactive decay of elements out there in the world. Those are things that really happen continuously. But for fun, we're just going to mess with it. So here we're going to use this formula that we didn't actually write in question 14. We're going to calculate the value after 20 years of a principal that was invested of $5,000. It was earning interest at a rate of 4% and it was compounded continuously, which tells us we're going to use this formula, not that A equals P times 1 plus R over N to the NT. So it's kind of a straightforward little formula. You just have to remember how to type this E into Desmos. And I will show it to you. There's a few little tricks here. So get ready. When we type it in, one of the things we need to be careful about is the exponent, especially when we're doing this multiplication up here, this 0.04 times 20. One of the things to be careful of, note, if I do 0.04 and then I hit the multiplication button, it drops the multiplication out of the exponent. We don't want that. If I put in 20, we get this ridiculous number. That's not correct. I need the multiplication to occur up here in the exponent. So one of the ways to do that is put parentheses there and then times 20, and that will get us the correct answer, which in this case, after 20 years, $5,000 turns into $11,000, $127.70. One other little note here, if we want to know how much interest did a compounded continuously, or any compounded more often than simple interest, what we need to do is subtract the initial principal. This would get us the interest, and I will write this down. So in this case, the amount of interest that was earned is $6,027.70. Let me scamper back to our paper. So generally speaking, if we want to calculate the interest earned in a compounded scenario, we have to take the future value and subtract from it the principal. Remember, back with simple interest, we could calculate it directly. It was just I equals PRT. So just be aware that this is how we calculate interest in a compounded situation. All right, we got one last little example here, and that is we're going to compare a simple interest to a compounded continuously. Looks like we're investing $50,000 for fun. I would love to have $50,000 to invest for fun. We're earning 6% interest, simple interest, and versus continuously, and we're going to do these different years. Well, remember, simple interest, the formula is A equals P plus PRT. Compound interest, the formula is A equals PE raised to the RT, and I'm going to do this in a table just like before. So I think I'll start with a whole new graph. I'm going to build a table, and I'm going to type into the table my two equations. So 50,000 plus 50,000 times 0.06 times x1. That's going to take whatever I put in here, which is 5, and then 10, and then 15, and 20, and 25, and 30. And then over here, I'm going to type in my compounded continuously formula. So here's my 50,000. Note I'm just hitting E, and that's putting in Euler's number. I'm going to raise that to the 0.06, which is the interest rate, and I need to multiply that times the amount of years, which in this case represents x1. And here's our two future values over that time. If I wanted the difference between those two, I could subtract them, but you can see clearly that the compounded continuously is beginning to take off quite a bit after the 30 years. A much better investment vehicle.